Every year, over 12 million cars reach the end of their life in the US, and worldwide, more than 50 million vehicles are retired. Left in junkyards, they rust, leak fluids, and occupy space. But in the world's largest recycling plants, nothing goes to waste. Steel, aluminum, plastic, and rubber are reborn. Trucks carrying the weight of 50 elephants arrive daily, feeding one of the most precise recycling systems on Earth. Buckle up. This is the journey from rust to molten steel, from scrap to new life. It all begins with collection. Cars arrive from junkyards, insurance write-offs, rental fleets, and corporate vehicles that have reached the end of their service. Each truck carries several tons of vehicles, carefully loaded and balanced to ensure safety and efficiency. When a truck arrives, it passes through multiple checkpoints. RFID scanners log the vehicle, high-resolution cameras capture its condition, and weight sensors confirm it matches the expected load. Every detail is recorded in the plant's central database, allowing engineers to schedule its journey through the recycling line with precision. Timing is critical. Even a single delayed truck can create a bottleneck that slows the entire system. Conveyors, forklifts, and autonomous guided vehicles, moving with millimeter-level accuracy, coordinate every movement. Human operators monitor the process from control rooms, while automated alarms alert them to any discrepancies. The process is more than just logistics. Workers visually inspect each car for unusual hazards, such as chemical leaks or improperly stored batteries. Specialized sensors detect residual fuel and identify vehicles that require extra care. This is a delicate balance between raw industrial power and meticulous precision. Every vehicle has its place in the workflow. Miss one, and the efficiency of the entire line is affected. Think of it as a giant puzzle or a choreographed ballet. Each car must enter the right sequence at the right time, or the rhythm of the plant falters. Across the plant, cameras and sensors communicate in real time, creating a network that is constantly learning, adjusting, and optimizing. It's a complex orchestration of machines and humans, all focused on transforming chaos into order. Once vehicles are on the line, dismantling begins. The first step is fluid extraction. Specialized robotic arms connect to drainage ports under the car. Engine oil, brake fluid, transmission fluid, and coolant are vacuumed into sealed containers. Each type of fluid is separated into dedicated storage tanks. Oil is filtered for reuse, coolant is chemically treated, and brake fluids are neutralized. Batteries are removed by hydraulic lifts. Lead-acid batteries are placed on reinforced pallets and transported to a separate line where lead plates and sulfuric acid are recovered. Modern lithium-ion packs from hybrid or electric vehicles are handled with additional safety shielding. Thermal cameras monitor battery temperature during removal to prevent overheating or fire risk. Tires are detached using automated debeading machines. Hydraulic arms grip the wheels, cutting the bead wires, while mechanical presses separate rubber from rims. Steel rims are sent directly to the metal line, while tires are transported for shredding and rubber recovery. Copper wiring, alternators, and electronic modules are stripped from the vehicle using cutting robots equipped with precision blades. Circuit boards are collected separately. They contain gold, palladium, and other rare metals. Strong overhead magnets lift large ferrous components, like engine blocks and suspension parts. Eddy current separators divert aluminum parts such as engine housings and wheel frames. Each material is deposited onto its own conveyor stream. Throughout dismantling, sensors scan for dangerous residues, unspent fuel, gas canisters, or pressurized airbags. Airbag modules are either triggered under controlled conditions or manually removed for safe disposal. This ensures no explosive materials continue down the line. By the end of dismantling, the vehicle is reduced to a clean shell, stripped of fluids, batteries, tires, electronics, and hazardous components. What remains is the car's body and major structural metals, ready for shredding. The car shells move toward the shredder line. These machines are among the most powerful in the recycling industry. A single industrial shredder is driven by motors delivering up to 4,000 horsepower, the same output as a small locomotive. Each vehicle enters the feed chute and is compressed by hydraulic rams to ensure a controlled feed rate. Inside the shredder, massive hardened steel hammers, some weighing over 200 kilograms, rotate at high speed. With each strike, the car's frame is torn apart. The shredding chamber is reinforced with manganese steel to withstand continuous impacts. As the hammers rotate, the car body is reduced from whole panels and frames into fragments no larger than 50 millimeters. Sparks and shredded metal fragments cascade into collection conveyors below. To prevent overheating, the shredder is cooled by circulating water and air. Vibration sensors monitor the machinery in real time. If a heavy, unshreddable object enters the system, such as an oversized gearbox or dense engine block, the system automatically reverses rotation to dislodge it before resuming. The shredded material is called automotive shredder residue, or ASR. Its composition is complex. Steel, 55 to 60%, aluminum, 7 to 10%, plastics, 10 to 12%, rubber, 5 to 7%, glass, 3 to 5%, residual fines and dust, the rest. Each fraction has its own recovery path. The steel fragments will be magnetically separated. Aluminum will be lifted by eddy currents. Plastics and rubber will continue to purification systems. Even glass shards are collected for secondary use. Dust control systems filter the air around the shredder line. Industrial vacuums capture fine particles and route them through multi-stage filters before clean air is released back into the plant. This ensures compliance with strict environmental standards and protects workers from airborne contaminants. From the outside, it may look like destruction, but this step is pure preparation. In just under a minute, an entire car body is converted into thousands of fragments, uniform in size, optimized for separation, and ready for the next stage of the recycling journey. After shredding, the fragments are transported by a network of conveyors into the separation line. Here, one of the most sophisticated material sorting operations in the world takes place. The first stage is vibrating screens. These heavy-duty machines shake the shredded material at thousands of cycles per minute. Larger fragments continue forward. Next, powerful magnetic separators remove ferrous metals. These magnets generate fields up to 1.5 Tesla, stronger than a medical MRI. As fragments pass under the drum, steel pieces are instantly pulled upward and carried away on a separate belt. Within seconds, tons of high-purity steel are diverted from the stream. What remains is a mix of non-ferrous metals and non-metals. Eddy current separators take over. Rotating magnetic fields induce currents in conductive metals like aluminum and copper. These metals are repelled forward into dedicated collection bins, while plastics and glass fall away. For plastics, air classification systems come into play. High-speed air jets blow lighter polymers upward, separating them from denser materials. Optical sensors scan color, transparency, and material type, activating targeted air blasts to redirect each fragment into the correct path. Glass fragments are isolated using density-based sorting. Vibrating tables and angled conveyors separate heavier glass shards from lighter plastic particles. Some systems add water baths to further refine separation, since glass naturally sinks while polymers float. Human operators provide the final layer of precision. Workers at inspection stations remove anomalies missed by automation, rubber-coated wires, mixed composites, or items too irregular for the machines. Every rejected item is redirected back into the process to minimize waste. By the end of this stage, the shredded mass has been transformed into clean material streams. Steel, at 98 to 99% purity, aluminum separated and ready for remelting, copper and wiring, bundled for refining, plastics, sorted by polymer type, glass, cleaned for secondary industries. This separation process transforms what once looked like industrial debris into neatly categorized resources. Every second, tons of material are sorted, purified, and prepared for the furnaces and recycling lines ahead. The purified steel fragments leave the separation line and enter the heart of the recycling plant, the electric arc furnace, or EAF. This is where scrap transforms back into raw steel. Each furnace is a massive vessel lined with refractory bricks, designed to withstand continuous temperatures above 1,600 degrees Celsius. The furnace lid is lowered into place, and 3 graphite electrodes, each the size of a tree trunk, descend into the chamber. When activated, the electrodes release arcs of electricity so intense they generate tens of thousands of degrees at the strike point. The shredded steel, now called charge material, begins to liquefy. Within minutes, solid fragments turn into glowing molten metal. Operators continuously monitor the process from a control room, where infrared cameras and real-time spectrographs track the temperature and chemical composition. To ensure quality, oxygen lances inject controlled streams of gas into the melt, oxidizing impurities like carbon, silicon, and sulfur. Fluxing agents such as lime and dolomite are added to bind unwanted elements. These binders rise to the surface, forming a floating layer called slag, which is later removed and used in road construction and cement manufacturing. Nothing is wasted. The molten steel is stirred by electromagnetic currents to ensure uniform chemistry. Once analysis confirms purity, the furnace tilts hydraulically, and the liquid metal flows out in a stream of incandescent light into massive ladles, each capable of holding over 100 tons of steel. From here, the steel can take 2 paths. Some goes directly to continuous casting machines, where it is solidified into slabs, billets, or blooms. Others are transferred to secondary refining furnaces, where alloying elements like chromium, nickel, or vanadium are introduced to create specialized steels for automotive, aerospace, or construction industries. Every cycle of the furnace recycles the equivalent of dozens of cars, consuming far less energy than mining and smelting virgin iron ore. Compared to primary production, steel recycling reduces CO2 emissions by 58%, conserves raw materials, and saves up to 74% of energy. What was once part of a crushed vehicle is now reborn as high-grade steel, ready to be reshaped into the infrastructure and machines of tomorrow. While steel takes center stage, aluminum and copper play an equally vital role in the recycling line. Both metals are far too valuable to lose, and their recovery saves immense amounts of energy. After shredding and separation, aluminum fractions are diverted into specialized smelting lines. Unlike steel, aluminum melts at just 660 degrees Celsius, less than half the temperature required for steel. This allows recycling plants to process huge volumes with comparatively lower energy input. Aluminum scrap is loaded into rotary furnaces, where it melts rapidly. Salt fluxes are added to protect the molten metal from oxidation and to capture impurities. Once purified, the liquid aluminum is cast into long bars or smaller ingots, each stamped and tracked for traceability. The efficiency is extraordinary. Producing aluminum from recycled scrap requires 95% less energy than refining it from bauxite ore. In fact, nearly 75% of all aluminum ever produced is still in use today, thanks to closed-loop recycling systems like this. Car doors, engine blocks, rims, even soda cans. All of them can be reborn countless times without losing quality. Copper, though present in smaller amounts, is even more precious. Wiring, motors, and electronics yield concentrated streams of copper scrap. These are shredded and then refined using induction furnaces or hydrometallurgical processes. High-purity copper cathodes emerge at the other end, ready to be drawn into new wires that will power homes, factories, and yes, future electric vehicles. Every ton of recycled copper saves the equivalent of 3.5 tons of CO2 emissions compared to mining. Even trace amounts are worth the effort, since copper is essential to everything from energy grids to microchips. In these recovery lines, nothing is wasted. Aluminum dross, the residue left on furnace surfaces, is reprocessed to capture every last gram of metal. Copper residues undergo secondary refining to extract tiny percentages that would otherwise be lost. As these streams are packaged into gleaming bars and coils, one fact becomes clear. Recycling doesn't just conserve resources, it safeguards the future. The lightweight aluminum of today's recycled car doors may become tomorrow's aircraft fuselage. The copper wiring stripped from an old sedan could carry current in the smart grids of the future. From rust to refined purity, from scrap to critical infrastructure, these metals prove that recycling is not the end of a car's life, it's the beginning of countless new ones. Steel, aluminum, and copper are the heavyweights of car recycling, but modern vehicles are also filled with plastics and rubber. Lighter materials that pose unique challenges, yet offer huge opportunities when recovered correctly. Tires are the first to be processed. Each one is mounted on a conveyor and fed into massive shredders, equipped with tungsten carbide blades. These machines rip apart rubber into coarse chips. A series of magnetic separators remove the embedded steel belts, which are recycled separately. The rubber continues its journey through granulators, breaking it down into smaller particles until it becomes crumb rubber. Fine black grains used to pave roads, resurface playgrounds, and even form artificial sports fields. The scale is enormous. A single plant can process millions of tires annually, preventing mountains of waste from piling up in landfills or being burned, which would release toxic fumes. Instead, old tires are reborn into useful infrastructure. Plastics present a different challenge. Cars contain dozens of types: polypropylene in bumpers, ABS in dashboards, PET in seat fabrics, PVC in wiring insulation. After separation, plastics are shredded, washed, and then sorted using advanced technologies like infrared spectroscopy, which identifies polymers by their unique light signatures. Once sorted, plastics are melted and extruded into pellets. These pellets form the raw material for new parts: dashboards, trim panels, underbody shields, and even non-automotive products like furniture or packaging. Recycled PET can even be spun into fibers, giving seat covers and carpets a new lease on life. The impact is significant. Recycling plastics consumes up to 80% less energy than producing new polymers from petrochemicals. Rubber recycling reduces demand for natural and synthetic rubber production, conserving both oil and agricultural resources. But perhaps the most fascinating fact: these materials can cycle through multiple lives. The same molecules of plastic in a bumper today could reappear decades later as part of a car interior, a home appliance, or even construction materials. Rubber from a tire may live on under the wheels of thousands of other cars, silently supporting journeys across entire continents. Where many see waste, recycling plants see potential. Every dashboard, every tire, every scrap of plastic has a future, reshaped, repurposed, and reborn. The final stage of the recycling line is not about shredding or melting. It's about precision and trust. Before any recycled material leaves the plant, it undergoes rigorous inspection to guarantee quality that meets international standards. Steel ingots, slabs, and coils are scanned by laser profilometers that detect even the smallest surface irregularities. Tensile strength is tested by powerful hydraulic presses that stretch samples until they break, ensuring the metal will withstand years of stress in bridges, vehicles, and skyscrapers. Spectrometers analyze chemical composition, confirming alloy ratios down to fractions of a percent. Aluminum ingots are weighed, stamped, and checked for porosity Using ultrasonic testing, copper cathodes are measured for conductivity, since even microscopic impurities can reduce efficiency in electrical systems. Plastics and rubber pellets are tested for density, melt flow index, and elasticity, guaranteeing consistency for manufacturers who will transform them into new parts. All this happens at lightning speed, with automation carrying most of the load. Optical scanners and X-ray systems sweep entire production lines, able to detect flaws invisible to the human eye. Every product that passes inspection is logged into digital systems, giving it a traceable history from scrap car to finished material. Once approved, materials are carefully packaged for global distribution. Steel slabs are stacked onto pallets and wrapped for transport. Aluminum ingots are bundled in massive blocks, strapped with steel bands. Copper cathodes are stacked like golden bricks, ready for shipment to cable manufacturers. Pellets of plastic and rubber are sealed in industrial bags, labeled with polymer type and production batch. The scale is staggering. A single plant can process up to 12,000 cars per day, sending thousands of tons of recycled materials across oceans and continents. From here, they will be reborn as new vehicles, infrastructure, electronics, and countless other products that drive our modern world. This final step ensures that recycling is not just about breaking things down. It's about building trust in materials that are as strong, pure, and reliable as if they were made from scratch. And often, they're even better, because they represent progress, efficiency, and responsibility. Every car, every component, every fragment leaves the line with a second life already ahead of it. ROM junkyards to furnaces, from molten steel to shining ingots. The journey of a single car shows us the power of human innovation. What once sat rusting in silence is reborn into bridges, vehicles, roads, and machines that will shape the future. Every step matters. Every fragment counts. Recycling is more than waste management. It is transformation. It saves resources, cuts emissions, and proves that progress doesn't always mean taking more from the earth. Sometimes, progress means reimagining what we already have. The numbers tell the story. Billions of tons of material saved, up to 95% less energy consumed, and countless emissions prevented. But beyond statistics, this is about vision. A vision where nothing goes to waste, where yesterday's scrap becomes tomorrow's strength. Next time you see a car at the end of its life, remember, it is not the end. It is the beginning of another cycle, another chapter. A vehicle that once carried people across cities may soon carry the weight of skyscrapers or power the electric grid of tomorrow. This is the hidden beauty of industry, turning rust into resilience, waste into wonder, scrap into steel. If you've enjoyed this journey inside the world's most advanced recycling lines, share it, comment your favorite stage, and subscribe to explore more industrial marvels. Because in the end, every scrap has a future, and every future begins with what we choose to recycle today.